Here we have an example of a transfer where we have a column transferring over a wall and onto two columns below. So we're going to look at the two different types of struts that may be used, and this is again one interpretation of it. So first we have the bottle-shaped strut on this side. So what we have here is a compression, and tensile node. And we have the angle here. Angle here of alpha. So alpha is, so this angle here is tan alpha equals 1 on 2 for serviceability and equals 1 on 5 for strength. So that'll change the axes of the bottle-shaped strut. So here we have, as it moves out there like that in the bottle-shaped strut, you'll also have a tensile force here. So in between these axes, as it's pushing out, we have tensile forces developing. And if this tensile force is greater than the tensile strength of the concrete, then we need reinforcement to strengthen up the wall and reduce the cracking. On this side, if we look at an idealized parallel sided strut like this, we're going to have something like, so it moves in like that, just straight, and then if we looked at it like that, no tensile forces are developed. But if you look at clause 7.2.1, prismatic struts shall be used only where their compressive stress field cannot diverge. So this is generally the case we'll be using. So for the formula, it's 7.2.3 is St times beta S times 0.9 times F dash C times AC. And the force here, we'll call that F. Computation. So we've got a load coming down from the column above, and then it transfers through two struts like that, and then we'll have a subsequent tensile force developing. And also from the two struts, we are going to have the bursting check, which will be 7.2.4 in the code. So in this example, we are going to use just a few numbers. So we got, say you got this from the load rundown, we've got a force of say 1,080 kilonewtons, and transferring down to these on this angle, an angle of 40 degrees, and an angle of 30 degrees. So using basic first year statics for sum of f of y and sum of f of x, what we come up with is, so sum of fy equals 4. We'll call that strut B, we'll call that C. So sine 40 FB plus sine 40 FC equals 1,080. What we end up is with this strut force being 1,000 kilonewtons, and this strut force equals 884 kilonewtons. And then for the tie force, we have, say, cos 40 times 1,000 plus that's a minus because it's going in the negative direction, plus cos 30, 884. So we end up with cos 30 times 884, 766 kilonewton tire force. Which we'll go into at the end. So first of all, the strut, as we mentioned, we have a bottle-shaped strut coming out like this and down and then back down. We'll cover the bursting reinforcement soon, but for the strut, best off taking the dimension, the smallest dimension to start off with. So you're going to have the node coming out like that. It'll go out like that, now like that, but we'll just take the most critical dimension, which will be this. So say if we've got a 200 thick wall and a say 500 thick column here, that means a strut will take as dimensions of 500 there. So the equation, as in the code, is psi st times beta s times 0.9 f dash c times ac. So here we have the capacity factor equals 0.6. You can look that up and find that in the code. Beta S equals 1 on 1 plus 0.66 cot squared theta. So theta being 40 degrees here. So we're going to have, so tan 40. 1 divided by answer to make it cot squared times 0.66 plus 1 and 1 divided by answer. So 0.52. Now as this angle becomes more vertical, the strut efficiency factor will become closer to 1. And then next we have the strength. Say 65 MPa, pretty strong concrete. And then AC, as we mentioned, is 200 inch page. So 200 times this dimension here, so 500. So the strut here will look something like, so out like that, and then around, in, and like that. So what we end up with the strut being the capacity equals 0.6 times 0.52 times 0.9 times 65 MPa times 200 times 500. So 1,825 kilonewtons. So our capacity is obviously greater than the action of 1,000 kilonewtons. Therefore, okay.